Okay, anybody have any homework questions you'd like me to go over? Yeah.
The one you just talked about throwing a ball up into a hoop and finding the initial position, I think it was 6.
Into a basket?
Yeah.
Like, okay, yeah. Okay, so I think that was 4.
Yeah.
Okay. So the idea of that one is the ball is thrown, shot from some height, and we know everything about the velocity when it's shot. So we know this angle is 60 degrees. We know this, I think, is 7.8 meters per second. And the trajectory is going to be something like that. And we know this distance is 15 feet. And, oh, I do have a calculator. Yay. Oh, but this one's out of batteries. Okay, well, let's see. So this is 15 feet. And this is 10 feet. So you have to convert those. And we're trying to figure out the height that it's shot from. And then we're trying to figure out I think the displacement vector from where it's shot to the highest point. Okay, so first we have to convert 15 feet and 10 feet. Okay, so 15 feet. 3.281 feet is 1 meter. Can someone divide that for me? 15 divided by 3.281? 4.57 meters. And then for 10 feet, it's going to be 2/3 of that, but I don't know what that is. Okay, thank you. Okay, so for the first part of the question, it's asking for that height h. So we'll choose our time equals 0 to be when it's shot, and our time final to be when it reaches the basket. And then I'll put the coordinate system the way I always do on the ground underneath the object at time equals 0. Any questions about those choices? Okay, and then we'll figure out what variables we know and what we're trying to find. We don't know time final. The acceleration vector is 0, negative 9.81. P initial, we know PIX is equal to 0, but we're trying to find PIY. P final, like it's more common that you know stuff about P initial and you're trying to find stuff at P final. This is sort of the reverse of that. So P final is equal to the stuff we just calculated, 4.57, 3.05. And then V initial is equal to the speed times the cosine and sine of the angle of 60 degrees. So that is 3.9 for X. And then for Y, what's 7.8 times sine of 60? Can someone calculate that for me? 6.76. And then V final, we don't know. Okay, so to calculate PIY, the equation we can use is 2AY times the quantity PFY minus PIY equal to VFY squared minus VIY squared. So negative 19.62 times 3.05 minus PIY. No, we can't use that. What am I, stupid?
It's so hard.
My dad said I'd never amount to anything, and he was right. Okay, so that equation doesn't work. But so I guess we're going to have to solve for TF first. So we can go PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. So 3.05 is equal to PIY plus 6.7. Ooh, that's not going to work either.
Does it matter if you use the Y or the X?
Yes, it does. So we are going to, usually, most often you have to use Y, but in this case we're going to have to use X. You're exactly right. So PFX is equal to PIX plus VIXTF plus 1/2 AXTF squared. Okay, so the thing that makes this problem hard is kind of, it's not using the usual relationships. They're kind of flipped around. But okay, this one should work. So 4.57 is equal to 0 plus 3.9 TF minus 4.905 TF squared. And so you can set this up as 0 is equal to negative 4.57 plus 3.9 TF minus 4.905 TF squared. And this is your A. Question?
Wouldn't A be 0 if you're...
Oh, God.
So it would be a-
Yes, you are right. Okay, I'm going to turn this around starting now.
Should go home.
Okay, that's what I always tell you not to mess up to it. The AY is negative 9.81, but AX is 0. Okay, so, well, this is easier to solve. So TF is equal to 4.57 divided by 3.9. And so what do you get for that? 0.17? 1.17 seconds. Okay. Now we can use that in this one. PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. So 3.05 is equal to PIY plus 6.76 times 1.17 minus 4.905 times 1.17 squared. And so you can solve for PIY, and I think what you get is 1.87 if I remember right. Okay, any questions about that? And then for the second part, we're trying to figure out, so now we need to figure out, all right, the displacement vector is equal to like a final position vector minus an initial position vector. But we're trying to figure out the displacement from where it starts to the highest point, not to where it goes through the basket. To draw this out, the displacement vector would be from the starting point there to the highest point. So that's the vector we're trying to calculate, okay? And in order to do that, we have to figure out, we already know the position when the ball is shot. We have to figure out the position vector when the ball's at its highest point. So we have to come up with an X and a Y component, okay? All right, well, do we have to choose our time equals 0 or time final to do this? We do have to choose the time final to be, because you can't ever calculate anything at an instant that isn't either your time equals 0 or time final. So since we're looking for information at an instant that wasn't one of our initial time, our starting time finals, we have to choose a new one there. So we can still keep our time equals 0 the instant when it's shot, but our time final now has to be when it reaches the highest point, okay? And we can still use the same coordinate system. So as soon as we decide that our time final is going to be when it reaches the highest point, there's one bit of information we know we're going to use. Do you remember what that is? We know we're going to use the fact that VFY is equal to 0, okay? The y component of the velocity is always equal to 0 at the highest point. Okay, so we calculated time final with our old definition of time final. We know what the stopwatch said, but we don't know what the stopwatch says when it reaches the highest point. So we can't include that. The acceleration is still 0, negative 9.81. The initial position, we know all of that now. It's 0, 1.87. P final, we don't know anything about, and we're trying to calculate both of those components. V initial is the same as it was, so that was 3.9, 6.76. And then we've been waiting all this time to say this thing we know, VFY is equal to 0, okay? Okay, well, right away we can solve for the y component of this. So let's use this one. 2a y component times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So negative 19.62 times the quantity PFY minus 1.87 is equal to 0 squared minus 6.76 squared. So PFY minus 1.87 is equal to negative 6.76 squared divided by negative 19.62. Can someone calculate that for me? 45 divided by 2.5.
2.32.
Okay,
2.33.
2.33. And then add 1.87 to both sides. 4, 2. So PFY is equal to about 3.2, right?
4.2.
4.2. Okay, so that's PFY. So now we're halfway there. We have to calculate PFX too. But there's no equation that'll let us calculate PFX. So again, we're going to have to find time final. We can do this with the equation VFY is equal to VIY plus AYTF. So 0 is equal to 6.76 minus 9.81 TF. And if you solve that, I think you get TF is equal to 0.69. Okay. And now that we have TF, now we can calculate PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 3.9 times 0.69 plus 0 because AX is 0. And so PFX is equal to, what do you get if you multiply those two? 2.69 meters. Okay, so finally the displacement, the blue vector that I drew here, is the final point, 2.69, 4.20, minus the starting point, 0, 1.87. And you get 2.69 for the x component and 2.33 for the y component. Okay? Any questions about that? Any other homework questions you'd like to see? Yeah.
Letter G on number 2.
Do you have it there in front of you? I can pull it up.
No.
Okay, that's fine. I'll just pull it up.
So one other small thing.
Yeah.
So to find the velocity for x and y, you just do the vector calculation. So for example, it'd be 7.8 times cosine of 60 for that problem.
Correct. Yep, exactly.
The y.
And then the y is 7.8 times sine of 60.
Okay.
Yep, exactly.
Yeah.
Which one did you say again?
Number 2G.
2G, okay. Oh, okay. Well, so this is something we're going to start doing a lot in the next couple labs. We haven't done much of it yet, though. But so to do this, I really don't have to do the calculation.
Did I try and there was something where I got stuck, so I looked at the answer
Yeah.
key and it gave me like two smaller velocity numbers and then it like a big one. It was
Okay.
like a big letter B and then like 28.
Oh, okay. The
And I
big,
wasn't quite sure how you got
Yeah.
that.
Okay.
That was what was confusing.
I gotcha. Well, number 2G. So once you do all these calculations, you see basically that the way this is going to work is this thing takes off at a 25-degree angle. I missed how fast it's going, but well, let's see. 28 meters per second, and from a height of 1.8 meters. So this path is going to go something like this. It'll start out with that velocity vector as tangent to it, and then it'll do this. And this is 1.8 meters. And G asks you to sketch the velocity vector the instant before it hits the ground. So what's the velocity vector here? Okay. Well, you can calculate that velocity vector, calculate both of the components, and then you can sketch the vector that you get. But notice that the path of the ball is also a graph that you can draw in the XY plane. So like if this is your coordinate system, and the velocity vector is going to be tangent to the path at this point. So there's a tangent vector to the path in the direction of motion, so this way. And so this would be the velocity vector. Okay. So at any point on here, if you wanted to calculate the velocity vector, like what's the velocity vector at the highest point? Draw a tangent to the path. Draw the vector in the direction of motion, so this way. And that's the velocity vector at the highest point. The velocity vector at the highest point, by the way, is always horizontal like that because it always has 0 y component. Is that enough on that one, or you want to go through the calculations too?
No, that's good.
Okay, and then as far as you said the capital V,
Yeah.
so I use capital V to mean the speed. It's the magnitude of the velocity. So remember that the speed is always equal to the x component of the velocity squared plus the y component of the velocity squared, square root. So that's how I calculated the speed there.
Got it.
I don't ask you to do that very often.
All right.
Any other homework questions you'd like to talk about? Okay. So last time, we introduced mass and force. And the reason we introduced those is so that we could define Newton's second law. And Newton's second law is the most important equation in this class. And Newton's second law says if you add up all the forces acting on an object, so I'm calling that F net, and remember forces are vectors, so what you get is going to be a vector. The sum of all these force vectors is going to be equal to the mass of the object times the acceleration of the object's center of mass. I'll just write it as A. We're still doing particles, so we're treating every object like it only exists at its center of mass. So I'm going to leave off the thing saying center of mass. But this is the sum of all the force vectors. M is the mass of the object. And A is the acceleration of the object's center of mass. In this class, there are only two types of forces that are going to act on things. So in this class, let's say forces can arise two different ways. The first one is weight. And the definition of weight is the force applied to an object by gravity. And the only other way that forces can come about is contact forces. So contact forces are forces that are applied by something touching the boundary of the object. Okay, so the way we're going to break this down is first we'll talk about the weight force, and then contact forces we're going to break up into three other types. But then that's every kind of force that we'll have to deal with in this class. So let's first think about the weight force. How can we figure out what force gravity applies to things? Well, we watched that video of somebody dropping a bullet and firing a bullet at the same time, and we saw that gravity is not affected by an object's motion. So we've seen that gravity is doing the same thing to an object whether it's moving or not, okay? So gravity is always just applying the same force to things, to a given thing. So, okay, no matter what an object is doing, gravity applies the same force to it. Well, that means that we can think of any situation we want to figure out what force gravity applies to something. So what we're going to think about is an object in free fall, okay? So imagine a 1 kilogram object in free fall. What are we going to take advantage of for an object that's in free fall? There are two things that are useful about an object in free fall. One is we know the acceleration. And the second one is there's only one force acting because it's not touching anything, okay? So the only force is the weight. And the acceleration is 9.81 meters per second squared. And I'm going to sometimes use this abbreviation for this number, this positive 9.81 meters per second squared. I'm going to call that lowercase g. And this force is acting down. I mean, this acceleration is acting down. So these are two things that we know about an object that's in free fall, okay? So now go to Newton's second law. Newton's second law. And we're going to try to figure out the force that's applied by gravity. We'll use a coordinate system with the y-axis pointing up. So this is going to be equal to 1 kilogram times the acceleration of negative 9.81 meters per second squared. And so if you multiply these out, 0 times 1 kilogram is 0. 1 kilogram times negative 9.81 is negative 9.81 kilogram meters per second squared is what we're calling newtons. I mentioned that last time. Or you could also think of this as acting that way with a magnitude of 9.81 newtons. Okay, so on this 1 kilogram object, the force that gravity applies to it is always 9.81 newtons. And we figured that out while it's in free fall, but that's also the force gravity applies to it while it's rolling or whatever, okay? Okay, so that's pretty good. So now maybe our first thought is, okay, gravity applies 9.81 newtons to everything. But let's think of something with a different mass, okay? So now let's do the same thing for a 50 kilogram mass. Newton's second law says the gravitational force is equal to 50 kilograms. What's the acceleration of a 50 kilogram mass in free fall?
Minus 9.81.
Yep. So 0, negative 9.81 meters per second squared. Multiply those together and you get 0 for x and negative 490.5 for y. Or in other words, a force of 490.5 newtons. Okay?
You don't have to put the negative if you're showing it.
Yeah, that's right. That's correct. So if you're showing the arrow, then all you have to put on it is the magnitude of that vector. Okay, well, so what we learned here is that gravity applies different forces to things with different masses, which probably isn't too much of a surprise, you know. So the more mass you have, the harder gravity pulls on you. Even though your acceleration is the same, you know? All things accelerate in free fall the same, but in order for that to happen, gravity has to apply bigger forces to bigger things. Okay, so in general, the gravitational force is equal to the mass times the acceleration of gravity down. Okay? So now let's think about, we're going to use what we know about the force gravity applies to things and try to sort of bootstrap from there to figure out what some other forces are that are applied to things, you know, some contact forces and stuff. So let's think of this as like an example problem. So let's say that there's a 100-kilogram man on a scale. What's the force vector the scale applies to the man? Okay, that's the man. And that's the scale. So this is kind of like how a scale works, you know? I mean, a scale, like, how would a scale know what force gravity applies to you? It doesn't, you know? But we're going to see that, that the scale applies a force to the man with the same magnitude as the weight force. And we'll do it through Newton's second law, okay? So Newton's second law for this says there are two forces now acting, right? There's the force of gravity, and there's the force applied by the scale. So the force of gravity is 0, negative 100 times 9.81. This is the force of gravity. We just figured out that that's what it has to be. And then we'll add on this vector. I'll call it F scale. And that's equal to the mass of the man, 100 kilograms, times the man's acceleration. If he's just standing there, no velocity, what's the acceleration going to be? Well, acceleration is a measure of how quickly the velocity is changing. So if the velocity is staying constant, there's no acceleration. So this is going to be 0. Okay? And so I'll rewrite this. I guess I'm going to rewrite this with an x component equation and a y component equation. The x component equation says 0 plus the x component of this scale force. So 0 plus, I'll call this F scale x is equal to 100 times 0, so 0. And then if you solve for that variable F scale x, you get that the force, the x component of the force applied to the man by the scale is 0. And now we'll go to the y equation. That says negative 981 plus the y component of this scale force is equal to 100 times 0, so 0. add 981 to both sides, and you get that F scale Y component is equal to positive 981 newtons. If you put this together, you get that the force applied to the scale as a vector has a 0x component and a positive 981 Newton Y component. So what direction is that? Up, yep. And so you can also think of it as an upward vector with a magnitude of 981 newtons. Okay, so the way this works is gravity, so you use a scale to measure the force that gravity applies to you. Gravity applies a force with a magnitude of mg down, and in order for you to have zero acceleration, if you're not touching anything else, the scale has to apply a force with the same magnitude in the opposite direction. Okay, so that's how a scale works, and that's why, so we're assuming two things for the weight and the scale force to have the same magnitude. We're assuming that the person isn't accelerating, and you know scales go haywire if you jump off the sink onto the scale, because when you make contact with the scale, you're accelerating. And so these assumptions don't hold, and it's not measuring your weight until things reach equilibrium, you know? And the second thing it's assuming is that you're not touching anything else. So like if you want to lose weight quickly, you know, you can hold on to the towel rack or whatever, you know? But because then the assumption that the scale's making that it's the only thing supporting your weight is wrong, you know? And so, anyways, that's how it works. Any questions about that example? Okay. Oh, one thing I said before was, so remember this, do scales measure force or do they measure mass?
Force.
They measure force, right. And there's always on a scale, there's conversions that let you see what your mass is based on your weight. But that conversion is assuming that you're on the surface of the earth. If you used a scale to measure your weight on the moon, it would measure that force accurately. And that force would be, like basically it would be the same as this, but your G would be much smaller than 9.81. So you'd get a much smaller force. But then the conversion the scale did to tell you your mass would be totally wrong, because it's assuming that G is 9.81. Okay, let's do one more example, because I can see this is exciting to you. Okay, so this time, let's say the same guy gets on the scale, but he's looking at the scale when he's on an elevator that's accelerating up. Okay, so 100 kilogram man. Okay, so let's say this guy is trying to make the football team, and his coach says he needs to gain some weight or whatever. So he's like, I'll show him, I'll measure my weight on an elevator. So okay, so there's the elevator. There's the scale on the floor of the elevator. Here's the man. I don't know why I always draw the man this way, only in this weight section. But I've gotten really fond of this guy over the years. Okay, and this elevator is accelerating up, let's say at 2 meters per second squared. So let's go to Newton's second law. there are two forces acting on the guy. There's a weight force down, and then there's a contact force from the scale. So just like before, we have 0, negative 981. And then we have the force applied by the scale. And that's equal to the mass of the man times the acceleration of the man. If he's just standing there in the elevator, then everything in the elevator has the same acceleration. So this is going to be 0, 2. I'll leave the units off this time. Okay, so the x equation says 0 plus f scale x is equal to 0. Bless you. And so this tells us that f scale x is 0. And the y equation tells us negative 981 plus f scale y is equal to 100 times 2, so 200. And now add 981 to both sides, and you get that f scale y is equal to 1181 newtons. So most of the time when you're going up in an elevator, going down in an elevator, it's moving at a constant speed. But right at the start of the motion, it's accelerating to get up to that speed. So during the part where it's accelerating, assuming the acceleration is 2 meters per second squared, which is probably in the right ballpark, that scale would give you a higher reading of the weight. It's not really your weight that's changing. It's the force that the scale applies to you. Okay, so the force of the scale is 0, 1181. So in this case, there's more force required. More force required than standing still. Anyone want to guess what the scale would say if the elevator was accelerating down? It would be less. And so how would that work? Well, if you go back to this equation, the only thing that would change is this would be, say, 0, negative 2. And so when you added the 981 to both sides, you'd be taking away from that, and you'd get, I guess, 781 in that case. Okay? So this is just kind of a glimpse at the kind of stuff we're going to be doing now with Newton's second law. Just little by little, we're going to kind of add layers of complexity onto it until we can do a lot of different kinds of forces. But before we get into too much more complicated stuff, I need to talk about free body diagrams. So free body diagrams, I'm going to abbreviate it FBD, free body diagram. And from this point forward, I want you to draw a free body diagram every time you use Newton's second law. And the purpose of the free body diagram is to just show all the forces that are acting on a thing. So you'll draw basically the thing the object that you're looking at. And then instead of including the surroundings in your picture, you'll just include the forces that those surroundings are applying to the thing, okay, to the object. So I'm going to give you a set of steps I want you to follow when you do these free body diagrams. It'll all get to be second nature because you'll do a bunch of these. So here is a set of steps. First, draw a closed outline of the object. It doesn't have to be artistic. It just has to show what the boundary is between the object that you're considering and everything else, okay? And this outline should have no internal details and no external objects. It's just a line that shows the boundary. No internal details or outside objects. Okay, so let's say that I'm going to do this with my force guy. So he's going to be the thing we're isolating again. I like his tank top. Okay, so a closed outline of the guy with no internal details or outside objects looks like this. Okay. What about that? No, that's not an outline. And the problem is that what we're trying to be is very clear about what's inside the boundary and what's outside the boundary. Okay, so don't do this. Don't do this. All you want is that boundary. And don't do this. And the problem is that with this last one there's ambiguity about what we're including. Are we including the top of the floor? You know, are we trying to calculate the forces that are being applied to that floor? And so we want to just be clear. No, the only thing we're concerned about are the forces applied to the man. Okay. The second step is draw a downward arrow from the middle representing the center of mass. And then label that arrow with either the weight if you know it, or you can write just mg. So you can do it either of these two ways. We know the weight force because we've been dealing with this for a couple example problems. So it's downward force of 981. Or you could also write a downward force mg. And then the third thing, the thing that we can't really do yet, and we're going to spend the next couple classes getting so we can do this, is at each place where the surroundings make contact with the boundary, at each place where the surroundings contact the boundary. Draw an arrow in the direction of the contact force. And label that arrow with a number if you know the magnitude of that force, or more often with a variable. Okay, so a complete free body diagram for this guy standing on the ground has a weight force down of 981, and then a contact force that, you know, because of the last couple examples, we know that this contact force is pushing straight up. So I'm going to draw it like this, and I'll label it as capital N. I'm going to use that a lot of times for the force that the ground applies to things, that capital N. And one thing I want you to notice is if I put the fancy shoes and hat on the N, I mean it as a variable. And if I don't put those on, I mean newtons. Okay? So if I write a capital N like this, that's a variable. If I write it just like this, that's newtons. It's a little confusing, but there's only 26 letters, you know, so sometimes you have to reuse them. Anybody have any questions about the free body diagram? Okay, well, what I want you to notice about the free body diagram is if you do it right, the free body diagram gives you the entire left side of Newton's second law. And so once you have that, then all you have to worry about is what's the acceleration? What am I doing with the right hand of the equation? So free body diagram gives the entire left side of Newton's second law. Okay, well, I said that the force types are broken up into the weight, and contact forces. There are three types of contact forces that we're going to see in this class. The first one is pushing contacts. The second is pulling contacts. And to know whether something's pushing or pulling, a pulling contact is one where the contact could be replaced by a small rope or cable or string or something, okay? And the same, you know, it would have the same effect on the body. So let's say the contact could be replaced by a cable. And then the third and last one is friction contact. And this one is only going to happen when an object is sliding along a surface. Anybody have any questions about that? Okay, well, let's stop there, and next time we'll get into pushing contacts and how to represent those in free body diagrams. And then once you have it in the free body diagram, we'll go to Newton's second law and talk about how to calculate it. And I'll have your test back on Thursday. Not the lab test yet, but the other tests.